Welcome to section 5.6, which is going to deal with our basic growth and decay functions. We're also going to learn something new involving solving differential equations. So the first thing we're going to talk about is our growth and decay functions. We have our basic growth and decay functions. You've seen them in different forms. In science class, we look at quantities. Anytime you see something with a subscript of 0, you know that's an initial amount. We've also seen it as our PERT formula when you're continuously compounding a certain amount of money. But the basic thing is your initial value is what's going to be multiplying your exponential. That K or that R is your rate of growth, that constant of proportionality. If it's positive, it's growth function. If it's negative, it's a decay function. And T is in time. Now, when you're looking at these two, time can be in seconds, minutes, years, days, weeks, whatever. When you're talking about money, time is going to be in years only. So let's just practice a couple of our favorite growth functions, or at least we hope they're growth functions, and those are the two that deal with money. When you're compounding continuously, you're going to use your PERT formula. Compound at a certain number of times, you're going to use this formula, where N is the number of times it's compounded. So when you're compounded more times, that's going to mean more money. So all we're doing is plugging those in. P is 1,000. Your R is 6.5%, so that's 0.065, divided by your monthly compounded, so that's 12 times a year. And then when you take it to the power, you're going to have to put that in parentheses. So 12 times the time, which is 100, or which is 10. So this one's going to be a pretty easy problem because you want to find out what A is equal to. So A is already solved for. You just plug it in your calculator. This is one of the few times we will be rounding to the hundredths only. Okay. Same thing over here. You're going to put your 1,000 in, your 0.065 times 10. Once again, you're already solved for A, so you just plug it in and poof, you've got your answer. Now don't forget to practice this on your calculators just to make sure that you're plugging it in correctly. Now we're going to use the same two formulas, only we are going to change what we're looking for. This time we want to find how long it's going to take for our investment to double. Okay, so we want to know time. Well, in both of the formulas up here, time is a power, so we're going to have to solve that exponential equation in order to find our answer. Now they didn't tell us anything about what we've invested, but that's okay. We want to know how long it takes to double. So this is our first formula, the one we used in part A. I don't know how much I invested, but I know I'm looking at when I have twice as much. They did give me my percent interest, and I am compounding weekly, so that would be 52 times a year, and then that's 52t. In order to solve for our exponentials, we've always got to get our exponential by itself, so I'm dividing both sides by p. Well, the nice thing about it is that p cancels, so I have my exponential is equal to 2, which makes sense because we're looking at how long it takes to double, so it should equal 2. I want to get in here at this power, so I'm going to natural log both sides, because when I natural log both sides, I'm allowed to bring my power down in front. When my power's down in front, now I can solve. And I'm going to solve it all at the same time by dividing both sides by 52 times 1 plus 0.055 divided by 52. I'm going to divide the other side by the same thing. 52, 1 plus 0.055 divided by 52. Eek! Got it in there. So time is going to be, and we're back to 3 decimal places. The only time we are not going to do 3 decimal places is when they specifically tell us or when we're talking about money. The more times you compound, the more money you're going to make. So likewise, the less time it's going to take for you to double. Your formula is a little bit easier. You're looking at 2p once again though. E to the 0.055t Once again, you're going to divide both sides by p. In order to solve for your exponential has to be by itself before you natural log both sides. I'm going to natural log both sides. The nice thing about natural logging in e is they cancel each other out. So I'm already 2.055t. I'm ready to divide through and find my answer. And time is 12.602 years. Once again, you're only compounding this a certain number of times, okay, weekly. That is a lot compared to annually, but your annual percent's only 5.5, so it's going to be pretty close to the same amount of time it takes to double. So I don't want you to think, oh, if weekly is 12, then continuously is 5. It just doesn't work that way. Now we've got the combo problem. Now notice I've told you this is a decay function, not that I wanted to ruin the surprise for you or anything, because you're going to find out pretty quickly that it is the decay function. For instance, it talks about a half-life. Half-life means the time it takes to literally cut the initial amount in half. So things are going down, things are getting smaller. This would be like your radioactive decay. So we are looking at our basic formula, and I just go back to Q of t equals Q sub 0 e to the RT. I don't know why, it just makes me feel a little bit better to have Q's instead of P's or C's. It's the same equation. Now this is very much like how much time did it take to double. When you're talking about a half-life, you're starting with Q sub 0. You want to know when you have half of that initial amount. Now looking at our formula, we don't know what the initial amount is, we don't know what R is, we don't know what T is. We have to start finding some of this information. So this half-life is going to help us find out what that R is or what that K is, however you want to refer to it. So half-life, that means we have half of what we started with. And it took us 5,730 years to get it there. That's a lot. Okay, we need to go ahead and divide through by Q sub 0 because it's on the same side as our exponential, and we need to get rid of that exponential as soon as we possibly can. So get the exponential by itself so that you may natural log both sides. So I'm going to natural log both sides. The nice thing about that e is that it cancels with my natural log. So I have the natural log of 1/2 equals r times 5,730. I'm going to divide through. And I'm not going to find out what that amount is. I'm going to leave it as the natural log of 1/2 divided by 5,730. The reason I'm not going to simplify that because I don't want to round it. I can only round one time per problem, and now is not the time. So that was my first equation, okay, and that helped me find that K or that R. Now the next equation here, if after 10,000 years you have 2 grams, what was the initial amount? That's our second equation. And our second answer. Okay, so we have 2 grams after, so 2 equals, and that is after 10,000 years. We don't know what the initial amount is. We do know our rate is the natural log of 1/2 divided by 5,730, and that is after 10,000 years. Now we want to find out what Q sub 0 is, so we're literally going to divide both sides by e to the wow power. And yes, that is the mathematical term for what we're doing here. All right, so I'm going to take 2 divided by e to the natural log of 1 divided by 2 divided by 5,730 times 10,000. And you're literally going to put it in your calculator just like I have it written. I do want to find out what q sub 0 is, but I don't want to round that answer because it now will ask me how much did you have after 1,000 years. So I'm going to need q sub 0 out several decimal places. At least a couple there. So I know this is grams because this is in grams. Okay, so there's my second answer to that second equation. And now the last part. How much did I have after 1,000 years? So how much did I have after 1,000 years? I'm finding q sub t. I now know my initial amount. Please do not use a rounded version on this. And then e to the natural log of 1 divided by 2 divided by 5,730 times 1,000, not 10,000, 1,000. It's already solved for the variable you're looking for, so if I go ahead and put that all in my calculator, and please try this, my amount after 1,000 years, so that would be 1,000 years, is going to be 5.941 grams. Now notice it's not a lot less than what I initially started with, but that's because I only had 1,000 years. Okay, it cuts in half after 5,730 years. So after 1,000, there's not going to be a lot less. So notice everything that we had to go through to get the process done. If they don't give you that rate, that R or that K, that's the first thing you will have to find. Okay, so notice that was the first thing we found right here. Then they asked us to find other information, and we found that as we went. But that rate is what you're going to be finding first. Now that was just kind of a little review of what we did in the past. As is this slide, you've got direct variation and inverse variation. Now the reason why we're reviewing this is because we are going to solve differential equations. They're going to be given to us in this form. If they use the word directly, and they may or may not use the word directly, they may say y varies as x, so it may have y varies as x. That means that you have some constant you multiply x by, and that will give you your y coordinate. Inverse variation, it has to have the word inversely. If it doesn't have the word inversely in there, then you got yourself direct, which is multiplication. Inversely is division. So let's see what they're going to have us do with all of this. Okay, a growth or decay function usually starts out as a rate of change, and that makes sense. So they may start off with this sentence here. So this is what they're going to start with, and then we have to write out the equation. Whoa, my line got a little out of control there, kids. Look out. So they give us an equation, or they give us a sentence. We write out the equation. The rate of change of y with respect to t, so that's our dy over dt, so that's that guy, is equal to, let me get rid of that. Okay, so the rate of change of y with respect to t, that's that guy, is your equal sign, proportional to the value of y. So notice they don't have the word inversely, so we know that that is direct, which means multiplication. Okay. Now when we have this differential equation, we are going to separate and integrate. Okay, so when they say to solve a differential equation, differential, that means you have a derivative. Solve it means you're going to find out what y is equal to. Okay, so notice it's going to be in this form here, or you could write it in this form, y prime. I prefer you write it as dy over dt. Now it was with respect to t, so that's why you have the dt on the bottom. So let's see what they're going to have us do here. Let me go back to that slide. Okay, so what we're going to do is we are going to look at this equation here, and we are going to integrate it We've got to do separation of variables. That means we're going to get y's and dy's on one side, t's and dt's on the other side. So when I'm looking at this, I've got dy divided by dt, so I'm going to multiply both sides by dt. Those will cancel. So now I have dy equals ky dt. I need to divide both sides by y to get it over to the other side. So now I have dy over y equals k dt. My variables are separated. Now I'm going to integrate. Now the integral of dy over y is natural log of the absolute value of y. Now they have a plus c, some constant, but when I integrate the left or the right side here, I don't have any t's. This is basically like 3 dt or 7 dt. K is just a constant, so when I integrate that, it's going to be kt plus c. Now this c is some mystery. We don't know what it is, so let's just lump it all together in one side. So this is going to become the natural log of y equals kt plus c. I want to solve for y. When they ask you to solve the differential equation, they want you to solve it. So in order to solve it, I'm going to e both sides. So that's going to give me the absolute value of y equals e to the kt plus c. When we multiply, we add our exponents. So this guy was once this guy. We still have that absolute value. Okay. And then this right here is just a constant. So we're going to rename it as c. Again, a lot of people will put c1 here and then rename this just normal c. Now through domain restrictions and so forth, you're going to see that this is just y equals c to the ekt, which brings us back to that original growth function. So let's just practice a couple of those, see what happens. Solve the differential equation, find the general solution. Now the reason why we're finding a general solution is we will still have a constant. So we will have a c in our problem somewhere. When we separate our equations, we're going to get our y's and dy's on one side, x's and dx's on the other side. So what I'm going to do is I'm going to multiply both sides by dx. I can't separate the 4 minus x. I can separate multiplication, division, but I can't separate addition and subtraction. So the left side's going to be dy, the right side's going to be 4 minus x dx. Once I separate, I'm going to integrate. The integral of dy is just y. Remember, I'm going to put the plus c just on one side. The integral of 4 is 4x. The integral of x is x squared divided by 2. And I'm going to put that mystery constant on the side because we don't know what that constant is. It can be 2, it can be negative 78. We don't know. But any of the mystery constants, we're going to put them on the same side and just have 1. So we have the general solution. We have a c, that's why it's a general solution. That is our answer. It's called solving a differential equation. Differential just means derivative. Solving means you're finding y equals. Now on number 5, I'd like for you to try this one. Now this one's just a little bit trickier. When you are solving this, they have y prime. I want you to start off with dy over dx. I want you to change that. And then that's x to the 1/2 power divided by 3y. When you solve this, only move as little as possible to the dy side. So it's 3y. We're only going to move the y. We want as little over here because we will have to solve this for y. So the more we move, the worse it's going to get. Okay? So you're going to integrate both sides. Okay? And we'll see what the answer is in class. Now this one's just a little tricky. Like I said, be careful. Now this one is very much like our first example that we did. We're going to separate and integrate. We'd want to get that dx away from our dy, so we'd multiply both sides by dx. We want to get that 1 plus y. Once again, addition, subtraction, we can't separate that. Now, as we're doing these, today they're not going to be so bad, but tomorrow when we do section 5-7, they're going to be a little more intense. And what I mean by intense, when I look at my left side here, I have to do a little baby u substitution. And the u substitutions we'll do are going to be just that, baby u substitutions. Not much work involved. So I would rewrite that integral as du over u. I had everything I needed. I didn't need to do anything else. I'm still going to integrate the right side. Didn't need any help there. So when I integrate the left side, I'm going to have the natural log of the absolute value of u, which is going to be the natural log of 1 plus y. When I integrate the right side, that's going to be x squared over 2 plus my c. You got to have a c on one side. You might as well make it on the side that counts. And once again, we're going to be solving for y, so if you want to put c sub 1 there, you're more than welcome to. It does not matter. But we know to get up here, we're going to e both sides. Okay, so we're going to lose our absolute values here because we know through our domain restrictions that they're going to give us, it has to be positive. And then that's going to give us e to the x squared over 2 plus c, c1. We're going to split that apart. Subtract our 1. And then our constant, we're just going to rename it. This is just a number. We don't know what that number is. So we're going to rename it so it's going to be easier for us to work with. The power is our x squared divided by 2. Minus 1 is not part of the exponent. Make sure people who look at your paper can tell the difference. Okay. Let's set one more problem up, and we'll see if you can work that, and we'll check that when we get back on the next day. I was going to say on Monday, but I don't want to let this all out. All right, so the rate of change of y with respect to x. So the rate of change of y with respect to x, dy over dx, varies jointly as x and L minus y. So that's going to equal some constant x times L minus y. It's direct variation, okay? As long as it doesn't say inverse, it's going to be multiplication. So even though it says jointly, it doesn't say inverse, so it's all multiplied together. So this one's going to be very much like the last one we did. We're going to separate our variables, which means we're going to divide both sides by L minus y. And L is just a constant, so it's just like the last example with a 1. Doesn't matter. And we're going to multiply both sides by dx. So the k isn't going to move. The x, that's the one you're going to be adding 1 to and dividing by that same amount. So we're going to integrate both sides. And it's going to be very much like the last one we just did. Okay, so give this a try. I'll give you the answers in class tomorrow.